Good morning. I hope everybody's doing okay. We're into the last couple of weeks. So I'm going to move into chapter 10 today, which is on molecular structure. But as a prelude to this, I'm going to go back and look at section 9.6, which is on the periodic table. And that section probably would have been best titled as multi-electron atomic structure. Most of you have gotten a rudimentary foundation in understanding the periodic table, but there's just a few things I want to say before we move into chapter. Chapter 11, right? Chapter 11. So we're going to skip chapter 10, and the reason for that is I might get this to a cursory view of chapter 10's material, but you're never going to have a chance to have the material in chapter 11. So, and you'll do the material in chapter 10 in great length and great detail when you take thermal physics. So that's my rationale for jumping past chapter 10 right now. So anyway, I want you to appreciate that thus far. Right, thus far, we solved rather completely. Right, we glossed over some of the more intense mathematical pieces of solving the hydrogen atom. But you definitely have more than just a flavor of that solution. So, and I want you to recall that the solutions to the time-independent Schrödinger equation, right, actually have two primary pieces, right? They have a radial piece, and they have an angular piece. And I'm just writing M here. That really is M sub L. And I'll put it in. Okay, there we go, for completeness sake. So, so for instance, if you go back and you look at 100, psi 200, psi 21, -1, psi 210, psi 211, etc. Right? These are solutions to the Schrödinger equation for the hydrogen atom only. And you will recall that when we talked about these solutions can be mapped onto the commonly used atomic orbitals for hydrogen. So this would be the 1s, this would be the 2s, and these three, right, will form the 2px, the 2py, and the 2pz orbitals that are commonly seen in say general chemistry textbooks. Okay, so and again, linear combinations of these were used to generate the real, right, the real 2px, 2py, and 2pz orbitals, right? Recalling that 2, 1, 1, and 2, 1, negative 1, right, are complex. Okay, so you get linear combinations of those to form the real 2px, 2py, 2pz orbitals. Now these solutions that are going to be used as a basis set for multi-electron atoms. And we know, at least for hydrogen, the energy is given explicitly by the principal quantum number n. Now, when we move into multi-electron systems, this is modified a bit, okay? Because again, we have a multitude of other interactions that are taking place. For example, the electron repulsion term. We saw the spin orbit interaction, and so there are other interactions that need to be looked at in order to give a more refined picture of multi-electron systems. If you read section 9.5, one can talk about the screening of the nucleus electron Coulombic interaction by other electrons that are in the vicinity. Okay, so there are screening effects, and so there's other things going on. But needless to say, when we move in what is called the central field approximation, energy is still given primarily by the principal quantum number n, but energy of electrons will increase with increasing L. Okay, and so we know in the hydrogen atom that's not the case, but that is the case for multi-electron systems. Okay, beautiful. All right, so the combination of N and L we're going to call the electron configuration. And we also need the Pauli exclusion principle, which we did great service to a couple of lectures ago. Pauli exclusion principle, which states that at most two electrons can occupy a single state. Well, I should actually not use the word state. I should say in this case a single orbital. Right, one spin plus 1/2 and one spin negative 1/2. okay? So in any one orbital, there can only be 2 electrons. So let's use these principles in order to look at some multi-electron systems. Now, you should have up on your computer a good periodic table as we go through this discussion. Okay, so again, most of you are at least qualitatively well versed in periodic table, but hopefully this little discussion will give you some connection between what we've done with the hydrogen atom Schrodinger equation and multi-electron systems. So if we look at hydrogen, which is Z is equal to 1, we know that electron will occupy the ground state, which is an S orbital. And again, I want you to always be thinking that this is a 1, 0, 0 wave function, right, in terms of things that we looked at previously. So the instant we go to another electron, right, so helium is Z is equal to 2, right, we ran into this problem before. We now introduce a electron repulsion term in the total Hamiltonian. But again, looking at the independent electron model, again, one would put each of those electrons into a hydrogenic 1s orbital, okay? And that orbital can accommodate 2 electrons, and so one would write the electron configuration as 1s2. Now again, this is a total approximation, right? We are saying that those 2 electrons are going to enter into s orbitals, right, that are other than being modified for the nuclear charge, are going to be totally described by hydrogen wave functions. Okay, and at that stage, we are now in an approximation game. Okay, but the approximation game is actually pretty good. All right, because the electron repulsion terms are normally small, and later on, for those of you going off perhaps into some molecular quantum mechanics, we'll see that these can be handled by what is called perturbation theory. All right, but for now, we're just going to use the hydrogenic orbitals. Now, I want you to appreciate that this orbital now is completely filled, right? And so we say that it's closed, and as a matter of fact, if it's closed, then it can't enter into any chemistry, and we say that that atom is inert. All right. So chemical properties are going to be totally, not totally, but primarily determined, right, predominantly determined by the outermost electrons, the ones that are least tightly bound. And we call those valence electrons. Okay, so the least. So we'll write that down. So chemical properties are determined predominantly by the least tightly bound electrons. And these are called valence electrons. And again, you might be familiar with that term from your exposure to some general chemistry. So now if we go to lithium, Z equals 3. And so now 1s2 is the first orbital, and it can only handle 2 electrons, so we got to go now higher in energy. And so then this will be 2s1. And it will be this 2s1 electron which will govern the chemical properties of lithium. Okay? If we go to beryllium, Z equals 4, and this is 1s2 and 2s2. Okay, and you might say, okay, well now these both of these orbitals are full, and you might predict that beryllium would not enter into a lot of chemistry because you might think that those electrons now can't form any bonds. But what happens here is that the energy gap, right? The energy gap between the 2s and 2p is small, and so there are ways that these electrons in the 2s orbital can actually occupy the 2p, and as a consequence of that, there will be electrons that will be in the valence state, okay, and can enter into bonding. Okay, so we can continue this game. We go to boron, which is Z equals 5. And that would be then a 1s2, a 2s2, and a 2p1. We go to carbon, which is Z is equal to 6, a 1s2, 2s2, and now we have a 2px1 and a 2py1. I'll call it 2px and 2py. And we see what happens here in carbon is that one might ask, how come the 2p orbital didn't fill with 2 electrons before filling another p orbital? And the reason for that is that electrons occupying 2 separate orbitals are actually slightly farther apart than when they're occupying the same orbital, and so their electrostatic repulsion is reduced by putting electrons into subsequent orbitals first before pairing things up. And that is known as Hund's rule, and we'll see some other examples of that as we move along, right? So one can continue this game. And if we look at fluorine, which is a Z equals 9, it would be 1s2, 2s2, 2px, 2py, and 2pz. And so there'd be 2 in here, and 2 in here, and 1 in the last p orbital. And then lastly, completing that row, we would go to neon, which is Z is equal to 10. That'd be 1s2, 2s2, 2px2, 2py2, and 2pz2. And now again, this is a closed shell, and you know that neon is inert, and it's actually one of the noble gases. Okay, so this is inert, and it's a noble gas. Okay, so that last column far to the left are the noble gases, right? We've seen 2 of them here. We saw helium, and then now we've seen neon. Okay, so again, helium is a noble gas as well. Okay, beautiful. So again, we can continue this game, and The orderings, if you look in your textbook, there's there on page 321 is the orbital ordering. Okay, so orbital energy ordering. Okay, and so we know that the 1s is less in energy than the 2s, less than energy than the 2p, less than energy to 3s, less than 3p. And the 3D and 4s are really close in energy, okay? We'll talk about that next. Less than 4p, less than 5s, less than 4d, less than 5p, okay, and etc. Okay, we won't need orderings greater than that, at least not in this discussion. Let's go up and look at what are called the first row transition elements. Okay, and they start with scandium, number 21. If we look at that row from 21 to 30, right, from scandium to zinc. So scandium to zinc, these are what are called the first row transition metals or transition elements. Okay, and so what happens in this row is you begin to see the 3D level being filled. So for scandium, which is Z equal 21, then this would be a 1s2, 2s2, 2p6, now not making distinctions between the x, y, and z orbitals. I should point out here, right, that we could very well go back here and have written any of these, right? So fluorine, for instance, we could have written this as 1s2, 2s2, 2p negative 1, 2, 2p plus 1, 2, 2p 0, 1, right? We could have labeled those using their designations in designations from the hydrogen study. But you've got to keep in mind that these are not real orbitals, right? They're complex, and so to get the pictures that we commonly see, that is, that a p orbital is a dumbbell shaped orbital, then this is real. That's a real orbital, and usually when we draw them, right, we know that electrons can be found pretty much anywhere in space. These are typically drawn at a 95% contour, which means that there's a 95% chance of finding the electron bound by that p orbital. Might the electron be out here somewhere? Absolutely, but it's going to be less than or equal to 5%. Okay, so again, when we look at those orbitals, they're real, and they represent 95% of the probability of finding the electron within that space. Okay, so back to scandium, right? So that's 2p6. It's going to be 3s2, 3p6. Okay, and what one would do here is one would fill the 4s orbital, and then you would have, so this is 10, 20, and 21, 3D1. All right. And so again, remember that the energy of these last two orbitals, very, very close in energy. And so your book, right, your book actually writes this as 3D1, 4S2. And I think most chemistry text will write it as the ground state being 4S2, 3D1. Okay, beautiful. All right, and then we can continue along, and I want to look at chromium. All right, so chromium is Z equals 24. And again, let's just look at the outer shell electrons here. So this is actually, right, so this is actually what is called an argon shell, okay? And so we can actually write chromium now as an argon core, right, an argon core. And then we have the 4s2, and then we have 3d4. Okay, that's what you would normally write. Okay, but what happens here is, remember in the D level, right? D is L equals 2. Which means that m sub L is going to be -2, -1, 0, +1, +2. We can actually form here, right, 5 real orbitals. 1, 2, 3, 4, 5. Okay, and we would normally think of putting 1 electron in each of those. But we have this empty d orbital here. And again, remember about electron repulsion being minimized by separating the electrons. And so what happens here is that you actually have chromium to be an argon core of 4s1, 3d5. And so it puts an electron in that last d orbital. And they all have parallel spins. Parallel spins. And this is another example of Hund's rule. Okay, so again, you can see how we can use the hydrogen orbitals with slight modification to build up the electron configuration of multi-electron atoms. All right. So I'm going to leave it now to you to read section 9.6. I want you to appreciate the electron configurations. Of the lanthanide, series, which starts at cerium, which is Z is equal to 58, to lutetium, which is Z is equal to 71, and the actinide series. And that starts with thorium, thorium, which is Z is equal to 90, to lawrencium, which is Z is equal to 103. And both of these series will be filling f orbitals, and the same rules apply. So there are some exceptions, and it gets a little hairy. Once we get into the lanthanide and actinide series, but there's no way that you would know the exceptions without knowing the exceptions. And again, they're primarily gotten through atomic spectroscopy. So anyway, I want you to look at that. Next lecture we will move into molecular structure, which is pretty cool. And again, some of you have gotten some of the rudiments in chemistry, but we will look more in the weeds of the underlying quantum mechanics. All right, very good, people. We'll talk to you later. Take care.